Greetings. Welcome to chapter 3. All right, this thing we're talking about gates. We're going to be looking at all the possible logic gates that we're going to have, and believe it or not, it's not going to be as hard as you think it is, but it's interesting. It's going to be fun. So let's get started. The AND gate. It looks like this. We have two inputs. We'll call them A and B, and the output's called a Y. Here's your Boolean expression. Notice it's the dot. The dot there. That's where you're going to get the confusion, because normally when we say AND, we think we're talking about a plus, but that's not true. It's a dot for the AND gate. So just kind of remember that's backwards. And we talk about a truth table. This is our first experience with a truth table. A truth table is the result of changing our inputs, changing A and B. Since we're talking this is digital, they can only be in two states. They can be on or off, ones and zeros. With 0 being off, my F1 is on. Or it could be 5 volts is on, 0 volts is off. However, we're set up to deal with it. It's convenient for us to just talk about being on and off. Well, here in this state, if both inputs are off, my output's going to be off. With an AND gate, the only time I'm going to have a true output is when the inputs both are on. One and A and B are on. Any other time, it's going to be a 0. So that's how you remember the AND gate. It's one, A and B both have to be on in order to get an output. Okay, in this case, low is 0, so both of them are low. Output's low. One's low, one's high, the output's low. Same thing, but only time we get a high is when both inputs are high. The OR gate. Here's where we do get into our plus. The OR gate. Notice it looks more like don't know what to call it, but it's these are the old style symbols. We don't use the IEEE. We'll use these logic symbols for this. There are other logic symbols that can be used. We will stick with these. We will stick with this one. That I always have trouble drawing that. But in this case, it's any or all. There we go. Here's the truth table for it. If anything other than 0, 0 is on, the output will be on. So the OR is anything, if anything is high, then the output will be high. In this case, they're both high, so the output will be high. One of them's high, so the output will be high. Both are low, it will be low. And then this one, high. Now this is one we talked about the other day, an inverter. Now this was just without this it's just called a buffer, but we talk about the inverter first because it's easier to understand. In the Boolean expression, when we put a dash over the input, that means not. In other words, Y in this case is not A. Some systems use the apostrophe after the letter, and I use that on the test some, the apostrophe, and you need to use it too, simply because we don't have a way of doing an A with a bar across the top in the test and on your keyboard. You can double invert, so that, you know, when you double invert it, it comes out to be the same. So like this, I have A here, I invert it. At this point, I have A naught. And if I invert A naught again, I'm back to A. So if at this point that's Z, and at this point this is Y, Z would be A naught, and Y is A. The NOT gate is set to invert or to negate or to complement. Yes, that is true. All right. The NAND. Now it is an AND gate. It is an AND gate with the NOT on the end. And that's the equivalent of AND NOT, or like this with the apostrophe. And the parentheses are required because then you're knotting that. If you did this, that's the same thing. That's no different. And the transitive properties, that would apply. Since I have knots there, I can do this and not the whole thing. Now, you would think it's going to be the opposite of the truth table. If we have an AND truth table, I have A and B, and Y, I get 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. You would think if I inverted that, I'd get 1, 1, 1, 0. That's what a NAND gate gives you. It is the and then NANDed, or inverted. The NAND gate is a way of doing it one thing, the equivalent of having A and B, and running that through an inverter. Okay, this is an AND gate. Low and low is going to be high. Low and high is going to be high. High and high is going to be low because it's high with the AND gate. And high and low again, it's going to be high because it's low on the AND gate. Next we have the NOR gate. I need to edit that out. We have the NOR gate. You know, if you had the OR, you have A and B. 0, 1, 1. Y with the NOR gate. 0, 1, 1. 1. When you knot it, it's 1, 0, 0, 0. There we go. Okay. Both of them are low. The NOR gate's going to be high. All the others are going to be low. The next gate is the exclusive OR. It has its own symbol, which is your plus from an OR gate with a circle around it. And it boils down to being something different. It's got A and B. That's 0, 0, 0, 1, 1, 0, 1, 1. Now if I were ORing this, I would have this, 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 and this. But the exclusive OR is an odd number of the inputs being true. Now, it's not apparent from this, and for some reason this doesn't show up in any of the slide decks. But it's all based on these. If I come up with 3, like we'll see in the next one, it's all based on the odd numbers. So all those are low, so it's going to be a low. I've got an odd number to high, so that one will be high. All of these are high, so it's an odd number of highs, it will be high. Here I have an even number of highs, so it will be low. So the exclusive OR is odd numbered of inputs that are high or high. The exclusive NOR is similar. It's just the opposite of that. So treat the lows. Odd number of lows will be high. There we go. Output's high when only the odd number of lows are high. The odd number of inputs are low, rather. So the X OR is odd number of inputs. Output is high when the odd number of inputs are high. If you put an OR at the end of the XOR, which is what this is, a not on it, then you get this one. Well, poo. The NAND gate can be used as a universal gate. For example, if I combine these like this, I have an A, my NAND, it's a very poor NAND, output here. By shorting that to the same input, I get a knotted function here. So that means at this point I've got a not A, not B, and then when I AND them and knot them again, that is the equivalent of an OR, A or B. Quiz. Now we can use inverters to convert gates. In other words, inverted ORs, things like this. Now remember, in this case, this is no different than having the little knot on the end. Same thing here. Now, we talked about this, IC stands for integrated circuit, TTL family, transistor to transistor logic. That's basically the way they talk to each other. Yeah. So you really won't see a standalone AND gate to put in a circuit. You'll have a IC with a bunch of them on it. You'll get a chance to deal with some of this as we go along. Now here is an 8-bit counter. Here's what it looks like on schematic output. We won't spend too much time with this because you're going to build something similar. here's a different set of symbols. We won't use these, so don't worry about them too awful much. And if you want to learn more about the basic stamp, take the microcontroller interfacing class. We do this. We do this all the time. That's the whole class. The whole purpose of the class is to explore this and build circuits that we use the microcontroller on the basic stamp to control the even move it around a little bit like a robot. Take that course. That course is a fun course. The microcontrollers are fun things. Basic. It's a student-friendly basic, but basic is a student-friendly language. It stands for Beginner's All Symbolic Instruction Code. And generally, those of us who are of a certain age, that was the first programming language we learned. The second one a lot of us learned was machine language, assembly language, which is what the basic program gets turned into before it gets put into the controller. Now this is true, but at the same time, there's a Raspberry Pi and an Arduino or another versions of microcontrollers that you can buy kits for and play with and work with. I'm not going to spend too much time on this simply because you get into this into the microprocessor interfacing class. And here's some of the language that's used in that and how to achieve that logic function. Again, don't worry about that too awful much for this because I won't go over that. For that, we talked about the AND or inverters and how to all the way down to how to use a NAND as a universal gate. We'll get more practice with this as we go along, as we do some gate analysis and some logic analysis. Thank you, and have a good day.